Okay, so let's kind of go through each one of these reactions, make sure everybody's kind of cool with what you should end up. Because basically, if you can do this, okay, this is a large, pretty decent portion of your final because it's writing chemical formulas, it's balancing equations, it's doing stoic, okay, all of these things. So if you can go through all of this and feel pretty good about life, you're okay. If you go through this and you go, man, I have no idea how to do these, it's not going to end well. So let's make sure everybody's cool. So on this one, on that very first one, you're going to take a pen that doesn't write, H2SO4, and sodium hydroxide. Okay, so this is what's called a neutralization reaction. You have an acid and you react it with a base. Okay, and there's a whole bunch of different ways that this can play out. This is just the simplified version. So basically, this is also a double displacement reaction. So out of this, and again, here's the bigger picture that I want you all to get, is the physical condition for this reaction to take place. You have sulfuric acid. It's a solution, which means you have these ions floating around. You have sodium hydroxide. It was also a solution. So these ions are floating around. So these are just going to switch places. They're going to switch places because Mother Nature gains something from it. If Mother Nature didn't gain something from it, the reaction wouldn't take place. So that's your overriding theme that I want you to get out of Chem 1. Hey, you see a reaction take place, Mother Nature gains something from it. If the reaction didn't take place, Mother Nature goes, I'm good, I'm not going to worry about it. So out of any neutralization reaction, you get two things. You get water and, in this case, a salt of Na2SO4. Okay? Then just balance it out. So what you should see is there's a 2 here. Okay? So what that means is that this ratio is 2 to 1. So in theory, it should have taken twice as many drops of sodium hydroxide to neutralize this as it did the sulfuric acid because it's a 2 to 1 ratio. Okay? So there's your basic equation. Out of any neutralization reaction, you get a salt and you get water. If it was hydrochloric acid and sodium hydroxide, you'd get water and sodium chloride. Okay? It's a double displacement reaction. There you go. So your net ionic, and I promise you, you got to do net ionics on the test tomorrow. Okay? Separate these things out. Oh, okay. Well, this becomes H plus, and you have SO4 2 minus, and you have sodium ions, and you have hydroxide ions. So water is a molecular compound, so that sticks together. Okay, so that's a new thing. It isn't a precipitate, but it's a new molecular compound. So your net ionic is just H plus OH minus yields water. Okay, that's it. There's your net ionic. Don't make it difficult. Okay. When you get to the second one, okay, on the second one, you're going to take zinc and you're going to react that with hydrochloric acid. Okay. So right away, oh, this is a single displacement reaction. Now, in terms of the bigger idea, tomorrow you're going to have access to that reactivity series. The reason this reaction took place is because zinc is above hydrogen. Okay? Zinc is more reactive. Zinc being more reactive, it comes in here and it kicks it out. Now, in theory, the copper didn't react. So, and it was odd because like literally about half the groups, we ended up with like the sleeves of copper, and the other half it just completely dissolved because of impurities. So if you put copper in hydrochloric acid, nothing's going to happen because copper is below hydrogen, but zinc is above it. So if you do the over-under game, zinc, elemental zinc, is going to kick out the hydrogen. The copper, the reason the copper didn't react is because of the fact that the copper is less reactive, therefore nothing took place. So that's another thing that you should be able to see. Oh, okay, here's a reactivity series. Oh, if the element's below hydrogen, nothing's going to happen. If the element's above it, it does. So this is why silver, gold, copper, the big three metals that we use in jewelry, are all below hydrogen because of the fact that it's not going to react with hydrogen, even in water or hydrochloric acid or something like that. This is why all the elements that we use to make jewelry are below hydrogen. Okay, so you're going to get zinc chloride and hydrogen gas. Okay, and zinc chloride, Mr. Grill, is ZnCO2, correct? Yeah. Okay, pay attention to the little things. Okay, ZnCO2. You get a balance it, boom, put a 2 here, there you go. On that net ionic equation, make sure that it is balanced on charge and make sure it is balanced on number of particles. Okay? Any net ionic equation has to obey 2 great conservation laws. It has to obey conservation of charge, it has to obey conservation of mass. Okay? So when you get done on that net ionic, here's how you can check that you did it right. Add up all the charges on one side, add up all the charges on the other. If they both add up to the same value, it's balanced. Count the number of particles on one side, count the number of particles on the other. If those add up, you're good. So what you should see, just to give you some idea, on that answer, on that activity number 2, question number 2, calculate the moles of zinc used, that should be around, this is an ish, but it should be around like 0.04, okay? It's not very many of them. And again, be consistent on how you write out these values. When you do that conversion, if you just say, let's just say you put 0.4, okay? It's a train wreck, okay? Because if you look at your numbers, your scale is, you have like you probably had something around 2.4 something grams of zinc, okay? Something around there. So this has 3 digits. So when you do that conversion over here, those first zeros don't count because they're like freshmen. They're just taking up space, but they don't count. So you need like 3 digits past the first non-zero digit, okay? So when you do that conversion, when you take your grams of zinc and divide that by the molar mass, this number here should be 0.0 and then like 3 digits past that point. Because that's how good of data that you have. So when you do that conversion, you need that number of digits as well. Okay. So then when you get to that backside, this is an ish. Okay, this is an ish. But your answer to number 6 on that theoretical yield of your zinc chloride, again, you're going to start with grams of zinc, moles of zinc, moles of zinc, moles of zinc chloride, moles of zinc chloride, grams of zinc chloride. So your answer to number 6, this is an ish, is around 5 grams, okay? And that theoretical yield, based upon the number of moles of hydrochloric acid, should be around 10, okay? So those are ishes, but it's going to be something in that ballpark. So your answer to number 6 should be around 5, the other one is around 10, okay? On your potassium chlorate one, on number 7, make sure that you have balanced that right. So you have a chlorate, COO3, decomposes into potassium chloride plus oxygen. How could you have verified that that decomposition reaction produced oxygen gas? What could you have done? Parker.
The match thing.
Yeah, what would have happened if you put a burning splint into an oxygen environment?
Glows brighter.
Glows brighter, okay? So this is why, if you look at the small miracles that allows us to be here having this conversation, the early atmosphere of this earth did not have oxygen. It wasn't until a specific bacteria started producing oxygen. And it's cool. We have a 22% oxygen environment, 77% nitrogen. When you look at reactions, nitrogen very, 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 very seldom is involved in reactions. Oxygens are very, very reactive. So if those numbers had been reversed, if we had had like a 77% oxygen environment and a 22% nitrogen environment, any fire would just burn completely out of control. Because what typically limits a fire is the availability of your oxygen, okay? So literally, I mean, if you've ever seen like a grass fire, if you've seen like a house burn, something like that, it's pretty impressive, okay? And that's with a 22% oxygen environment. Imagine if you had a 77% oxygen environment. Your fireplace would go, you burn wood in your fireplace, boom, it would just go up like that, okay? So it's cool that we only have that percentage. So anyway, so on number 7, this is an ish, okay? So that answer to number 7 on your potassium chlorate one should be around 1 gram, okay? Something in that ballpark, depending on what mass of potassium chlorate that you started with. And then the mass of the metallic chloride, that should be around 1.5, okay? When you get to number 4, that's with the copper and the iron. So, again, your net ionic on number 2 should balance on charge, and it should balance on number of particles, okay? So, make sure, Izzy, on your net ionic that you have put the charges, okay? Because there's a big difference between Cu and Cu2+, okay? Cu is a chunk of copper, like a penny. Cu2+ is an ion that exists in water, and they mean completely different things, okay? Completely different things. So on number 3, that the copper from the copper sulfate, that should be an ish around 2.5 grams. And the iron should be able to produce a little over between 1 and 1.5 grams. So that first answer should be around 2.5. The second answer should be between 1 and 1.5 grams. And remember, you can only produce the smaller amount. On number 7, the last question on the bottom of page 3, you want to calculate molarity. You have to know molarity. That answer on number 7 should involve a lot of 7s for your molarity. I wish I was clever and said I worked it out that way, and that was on purpose, but it just was random. Anyway, anything you want me to go over that at all you have questions about? Yes, ma'am.
Number 9 and 10 on experiment 3.
9 and 10 on experiment 3. The theoretical mass of metallic chloride?
Mm-hmm.
Okay. So here's the deal. I hate my pen today. How many grams of potassium chlorate did you start with?
2.59.
2.59. So you have 2.59 grams of KClO3. Make sure that you have put what these are. Are they grams? And then is it KCl? Is it KClO3? What is it? So here's the deal. So you got grams of KClO3 here. So you're going to put grams of KClO3 here, right? Mm-hmm. 1 mole. Now, in this case, your metallic chloride is going to be your potassium chloride. So you're going to put moles of KClO3 here, and then moles of KCl up here, okay? And then you're going to have 1 mole of KCl, and then the molar mass of KCl up there. So you can go from grams of potassium chlorate to moles of potassium chlorate. Moles of potassium chlorate into moles of KCl, moles of KCl into grams of KCl.
Okay.
Got it?
Yeah.
And then you can do the same thing on number 10, on number 9. And then, there you go, that's all you got. Okay?
Thank you.
All right. Anything else? Grace?
Okay, so on number, activity 4, on number 7, like where are we getting the, where are we getting the amount before the iron was added? Like which one is it?
Okay, so if you go back to the instruction side packet, look at that and you'll see that you measured out 6.2 grams of copper 2 sulfate. So remember, at the end of the day, molarity is moles per liter. True? So you're going to start with the 6.2 grams of copper sulfate. Change that into moles of copper sulfate. Then take that 50 milliliters of water, convert that into liters, divide it out. So that's how you're going to know how much copper sulfate you started with, Grace. Just go back and look. Just go back and look at the lab itself and the instructions. Okay. All right. Anything else? Anything at all? Going once? Going twice? So I don't need the instruction packet. Okay. The only thing I want is the packet that has all of those calculations in it. So, get that handed in. This is the periodic table. Okay, so as you prepare for your final tomorrow, let's go kind of old school and talk about some different things. And yes, everything that we've covered is fair game on this. Yes, you'll have the review, we'll talk about that later. So let's say that I give you these 3 chemical symbols. Zinc 66, zinc 68, zinc 66, 2 plus. What's the difference between the first 2? One has 2 more neutrons. So let's talk about this number up here. What do you call that number up there? It's either the atomic number or it's the mass number. Mass number. So the number up there is the mass number. And your mass number is the total number of or nucleons. Okay? I hate this pen today. So that's the number of protons and neutrons. So, what do you know about neutrons? Do neutrons have, I'm about to throw this pen through the wall. What do you know about neutrons? Are they big particles? Are they small particles? Do they have a charge? They're big and they have no charge. So these are like the St. Bernards of the atomic world, okay? They're big, they're lumpy, they just kind of lay around, but they're important because they maintain the stability of the atom. So when you change the number of neutrons, you don't change the charge, okay? But you change the mass. So Now, that 30 down below. Ella, what do we call that 30 that's down below?
Atomic number.
Fantastic. And what does the atomic number represent?
Number of protons.
Number of protons. Cool. So, Raman, I have a mass number of 66. I have an atomic number of 30. So how many neutrons are there in that this first zinc right there?
Oh, I don't know.
How many neutrons? Let me ask you this. I owe you $66. I've paid you back 30. How much do I owe you yet?
36.
36. So 66 is the total number of protons and neutrons. So if there's 30 protons, there has to be 36 neutrons. Okay? So this one's going to have 38 neutrons. Okay? So these are isotopes. Remember, isotopes have the same atomic number, the different mass numbers. Okay. So these two are isotopes of each other. Addie, how many electrons are in each one of those atoms? Do not make this difficult.
0.
Okay. Atoms are neutral, right? So what's, Addie, let's back up. What's the charge on an electron?
1 minus.
Negative, right? All electrons have a negative charge, okay? All protons have a positive charge, and they're equal and opposite. So since this doesn't have a charge, which means that it's neutral. So if there's 30 protons, how many electrons are there? It's neutral. So charges have to balance out. If there's 30 protons, there has to be 30, okay? 30 electrons. That's what means it's balanced out, right? Because it's just like a dance. If you have 30 guys, there's 30 girls, everything balances out, it's neutral. So if you're not told an oxidation number, you just have to assume that the charges are balanced out. So, Peyton, this one has a charge of 2 plus. So how many electrons does this one have? Either 32 or 28.
32. 28.
28. Can you tell by the scrunchy face? Because here's the deal. Remember, a positive oxidation number means that you have more positive charges than you have negative charges, right? So this means this is lost 2 electrons. So let's talk electrons. Make sure that you can use your periodic table to figure out information. So let's go old school. So what are the 4 sublevels in an atom? Let me give you a hint. The first one is S. So there's S, so what's the next sublevel?
P,
P, then,
D,
and then
F.
F. Okay, SPDF. So let's say you're on the test and I ask you, hey, how many electrons can an S sublevel hold? And you flip out and you think, oh, God, I got nothing. Okay? Look. Here's your S sublevel. How many columns are there?
2,
2. So how many electrons can you put in an S sublevel?
2,
2. Okay. P sublevel. Miles holds how many electrons?
4, 6.
6. Okay. And if you're not sure, go over here, count 1, 2, 3, 4, 5, 6. Oh, 6. D sublevel, you're filling that. Count across there. There's 10. F holds 14. Okay. SPDF. If you're not sure, look at the periodic table. Don't try and memorize everything up for this test. Okay. Use the information that you have available to you. Okay. So that's the number of electrons. So how many orbitals, let's back up a little bit. What's the maximum number of electrons that you can put in any orbital? 2. Okay, maximum number 2. No matter what the orbital is, you can only hold 2. So the S sublevel, remember, only has one orbital. Okay, and that's the simplest one because if here's the nucleus, that's a spherical shape. So S has a spherical shape. Okay, it's the simplest. Mother Nature goes, okay, I'm gonna deal with that first. So Mr. Grill, how many orbitals then are in the P sublevel? 3. Okay, and so those are like pear-shaped. So there's 1, there's 2, and there's 3. Okay, those lay on the axis, like an x-axis, a y-axis, and like a z-axis. Okay, so here's an orbital, there's an orbital, there's your third, boom, x, y, z, 3 orbitals. D is going to have 5. Those get weird because they exist in between. F is even weirder because that's like a donut shape wrapped around P orbitals. Okay, I'm not expecting you to know that. Just general background information. Okay, so you can use that shortcut. So let's say that I ask you to write the electron configuration for, say, calcium. Okay, so if you want to write the electron configuration for calcium, here's the shortcut. Go to the row above calcium and find the noble gas in the row above calcium. So, Ella, you're close. What's the periodic table? Look at your periodic table. What is the noble gas in the row above calcium?
Argon.
Okay. So, what's the atomic number of argon?
18.
18. Okay? So that gives me 18 electrons right there. Okay? So there's that core. So, Ella, since you're there, what's the atomic number of calcium?
20.
20. So that gives me 18 of the electrons. So I just need to account for the last 2, right? So, find calcium. What's the number to the left of calcium that's out there on the side?
19.
No. Out there on the side. Like, what's the number of the row that involves calcium? Is it 1, 2, 3, or 4?
Oh. 2?
No.
What? I don't have one.
Okay. Over here to the left, if you look at this,
4.
4. Okay, there you go, 4. So remember, that 4 tells you the highest occupied energy level. So that's going to be argon. There's 2 across, and then you have 4s2. Okay? So let's talk Lewis dot structure. So if you have calcium, how many dots are going to be around calcium? 2, because there's 2 valence electrons. Okay? Now, this is why calcium has a charge of 2+, is because what calcium wants to do at the end of the day, calcium wants to get rid of those electrons so it can look like argon. Now, if it loses those 2 electrons, does it actually become argon since it has 18 electrons? Parker,
No,
why not?
because it's still got the number of protons.
Because remember, it is only the number of protons that defines the type of atom. It can get rid of 2. It's cool. Okay? It's the most stable form of that arrangement. But it doesn't become argon because you haven't changed the number of protons. You change the number of protons to 18, hey, then you're off to the races. Okay. First ionization energy. Okay, so we're going big picture here, old school. But it all kind of fits together. So first ionization energy. Remember, that's the energy it takes to remove the most loosely held electron. So as you go down a column, what happens to the size of the atom? Does it get bigger or does it get smaller? Emma, as you go down a column, what happens to the size of the atom?
Yes. Bigger.
Yeah, because it's like you're adding layers to an onion, right? So, and the quintessential one is like the alkali metals, lithium, sodium, potassium. As you go down, that single electron is getting further and further and further and further and further from the nucleus, okay? Cool. So you got that going, right? So, Keaton, as you increase the distance between the nucleus and the electrons, what happens to the attractive force between that nucleus and that electron? Gets smaller, because you're dividing by r squared, right? Okay? So, as you increase the distance, the attractive force becomes smaller. This starts a whole cascade of things, okay? So, as you go down a column, that electrons get further and further and further and further and further away, which means the attractive force becomes less and less and less and less and less. As the attractive force becomes less and less and less and less and less, it's easier and easier to take away that electron, so it doesn't take as much energy. So as you go down a column, first ionization energy becomes less because that electron is further away. Okay? Now, the other big trend is electronegativity, okay? Which is the willingness basically to take in electrons. Okay? So, if you look at electronegativity, okay, as you go down a column, electronegativity becomes smaller because of the fact that it's further from the nucleus, therefore it's going to be less and less willing to take that in. The halogens have an exceptionally high electronegativity. Okay, so why do the halogens have an exceptionally high electronegativity? Miles.
Because they have. Wait.
Keep
The
going.
halogens. I'm sorry. I'm just gonna make sure. Halogens are the 18th group, right?
17th group.
17th. Oh, because if they gain one more, then they'll be at the perfect amount of electrons.
Fantastic. Okay, so halogens have a very, very, very high willingness to take in electrons because they have 7 valence electrons. So if they can get one more, they're going to become like the noble gas. So halogens have an exceptionally high electronegativity. They have 7 gain pieces. They only need one more. They're going to take those in. Now, the noble gases. Grace?
Hold on. So would like fluorine have the highest?
It does, because that's closest to the nucleus. So that's because it's closest to the nucleus, that's going to be the strongest ability to take that in. Okay? Chlorine still wants to take it in. Now, this is where it becomes big picture. Let's say that you have a single displacement reaction. I'm going to give you 2 options. Situation number 1, I hate this thing with a passion today. You're going to take fluorine gas and you're going to bubble that into a solution of sodium chloride. Okay? Situation number 2, you're going to take bromine and you're going to put that into sodium fluoride. Okay? Both of them are single displacement reactions. One reaction will take place, the other one won't. Which reaction will take place and which one won't? Izzy, which one of those reactions will take place, the other one won't?
Okay, let me get my little sheet here.
All you need is the periodic table to answer this question.
Okay,
The first one will take place.
Spot on answer. Why?
Couldn't tell you.
Okay. Where's the most reactive halogen? At the top or at the bottom?
The top.
So fluorine is more reactive than chlorine is, right? So fluorine comes along and it comes up to the chlorine and says, yo, I'm more reactive than you are, get out. So what's gonna happen here is that you're gonna form sodium fluoride and fluorine gas, because the fluorine is more reactive, okay? So it's gonna take that electron, it's gonna take the place of it, and it's gonna kick it out. So this is like a senior coming up to a freshman and going at the dance, going, yo, mind if I dance with your date? And they go, fine, here you go, okay, because it's more reactive. Now, bromine, because it's further down, is less reactive. So that reaction won't take place. You put bromine in sodium fluoride, absolutely nothing is going to happen because Mother Nature doesn't gain anything from it. Okay, so that's your overriding theme. Mother Nature is a lazy prima donna. You will only do what is easiest for Mother Nature to do. Okay. Let me see. Why do the noble gases have no electronegativity?
Because they already have 8 electrons.
Fantastic. They're lazy. They don't need anything. They're snobs. They're going, peasants, go away. I don't need you. Okay? Because they already have the full outer shell of electrons. They don't need to take anything in. They're at the bottom of the energy well. Nothing's going to happen. Okay. So those are the big ideas. Okay? So in terms of the test tomorrow, it's almost all multiple choice. Okay? So what I have for you is yonder. Hold on, I just had it. So this is kind of the summary of what you need to know, okay? And the only thing you don't have to worry about is these titrations, because we really didn't have time to get there. You actually know it. Titrations are just a neutralization reaction between an acid and a base. So what you guys technically did yesterday, when you took the sodium hydroxide and the sulfuric acid, that was technically a titration, because you start with an acid and you add the base until it gets neutralized. So that's a titration. It's not a big deal. So there's two distinct parts. There's basically behind the second semester. This has the 5 types of reactions, ionic, molecular, naming them. On your acids, big ones you're going to need to know are nitric acid, hydrochloric acid, sulfuric acid. Those are going to be the big probably. What's the difference between an ionic bond and a molecular bond? Mr. Grill. What's the difference between an ionic bond and a molecular bond? Let me give you a hint. Ionic bonds form, starts with the letter I, ends with ons. Yeah, okay. Ionic bonds form ions, which means something is, you have a negatively charged ion, like chlorine, fluorine, one of the nonmetals, and it comes up to one of the metals, sodium chloride, or sodium, something like that, and says, hey, mind if I take your electrons? And Mother Nature goes, yeah, this is going to work out because I end up at the bottom of the energy well. So sodium chloride, okay, is going to be an ionic bond, because chlorine has a very high electronegativity, sodium has a very low electronegativity. Difference between those two is pretty large. It forms an ion. The chlorine takes the electron. The sodium gives up the electron. So an ionic bond occurs between when you have a high electronegativity difference and when you have a metal and a nonmetal. That's the easiest way to view it. It conducts electricity. Okay, so remember we did that conductivity probe. You know, you put that in there. Okay, got all that. Molecular compounds, that's when you have like typically 2 nonmetals, like for example carbon dioxide. Okay, remember when you name molecular compounds, this is when you have to have the prefix, because of the fact that, oh hey, here's the prefix. I have to name them because there's more than one combination. So carbon dioxide is CO2. CO is carbon monoxide, because carbon and oxygen can combine in different ratios because they're sharing electrons. So this is why you have to put the prefix when you're naming molecular compounds. But if I just have sodium chloride, okay, sodium chloride can only exist as sodium chloride because it has to balance out the oxidation numbers and they have to add up to equal to 0, okay? So this is why I'm not going to name that sodium monochloride, because it can only exist in one ratio. Carbon dioxide, carbon monoxide, I use the prefixes because there's more than one combination. Why don't I name sodium chloride sodium 1 chloride?
Because it only has one oxidation state.
It's true, because it has that one outer shell electron, it wants to give that up. So remember, the elements that have more than one possible oxidation state tend to be in the middle, okay? Lead, copper, iron, those are going to be the big ones, okay? So there's that. Here's basically the version of moles mole. When you do molar mass, volume, here's the 22.4 liters. Particles, Avogadro's number 6.02 times 10 to the 23rd. Remember, we have Avogadro's number 6.02 times 10 to the 23rd because it takes that number of particles to equal the relative atomic mass in grams. So if I said, hey, Parker, I need you to measure out 12 grams of carbon. Got it, Mr. Burkamp. That's going to be 1 mole. And then I said, Parker, how many atoms are there? He's going to say, oh, that's 6.02 times 10 to the 23rd, because it took that number of particles put into a pile to equal 12 grams. If he doesn't have that number of particles, he doesn't have 12 grams, okay? So that's why it's 6.02 times 10 to the 23rd, because it takes that number of particles to equal the relative atomic mass in grams. Okay, so there's that one. The other one you're going to get, this is for, basically, this is the first half. So you got atomic structure, protons, electrons, atomic number, mass number, atomic symbol, atom versus ion versus isotope, electron configuration examples, orbital diagrams. Remember, on your orbital diagrams, that's when you were going to go, like for example, if you wanted to do carbon. So carbon is 1s2, 2s2, 2p2. That's when you come in here and you go your up arrows, your down arrows, and then P has 3 sublevels, and you put 1 electron in each one. Okay, so that's what it's talking about with those. Cation versus an anion. Cation, remember, has the positive charge because it gave up an electron, so like sodium chloride, the cation is sodium, the chlorine is your anion. Here's your terminology: ionization energy, electronegativity, atomic radius, ionic radius, reactivity. So remember, like let's say for example, here is the sodium atom, okay, relative size. You have 11 protons and you have 11 electrons. The sodium ion is much smaller because it has 11 protons and only 10 electrons. So that atomic radius is smaller when it forms an ion for 2 reasons. Number one, you lost the outside layer of the onion. So now you have, that's gone. The other thing is that now you have 11 protons pulling on 10 electrons. So there's more of an attractive force on each electron. So it's just like you go to the zoo. You have there's 11 parents and there's 11 kids. It's cool. Okay, everybody's balanced out. Timmy, who's on the outside edge, gets too close to the lion cage. Sorry, Timmy. Okay, Timmy's no longer with us. What happened to Timmy? Don't know. All I know is the lions are pretty happy right now. So what's going to happen is that the parents are going to pull in those remaining kids even tighter, because now you have 11 parents pulling on 10 kids, and you don't want to lose another one. So the opposite happens, though. If you've got 11, let's say, for example, you have fluorine. Fluorine, 7 protons, 7 electrons. Oh, it's going to gain an electron. So now you have an extra kid. So anions tend to get bigger because you've added electrons, so it's like a bigger cloud. Cations become smaller because you have more of an attractive force. So here's the little thing: moles, particles, molar mass, okay? Just a different way of looking at the same thing. Coulombic attraction, okay? Remember, that's what's going to happen here. Coulombic attraction is a fancy word for saying, hey, how attracted are the electrons for the protons? There's two factors. The two factors are the number of particles and distance. The more particles there are, the stronger the charge. The greater the distance, the weaker the charge. So there's a direct relationship there. Gas laws, okay? Simple idea on gas laws. If you increase the number of particles, you increase the pressure. Think of this in terms of the second grade classroom. I put more kids in the classroom, the pressure is going to go up. If I shrink the size of the classroom, the pressure is going to go up because I'm going to have more collisions. If I give Skittles to the kids, the pressure is going to go up because you're going to have kids going, I love Skittles! Okay, and Timmy's going to be very excited and they're going to bounce around because they have more Skittles. So there's all of that. Okay, so here's the deal on this. Everybody's going to get these, okay? I'm going to give you all of these. If you want to use them actually on the test, if you want to use these as a resource on the test, here's my criteria. So some of you have already contributed to, you bought solar merch, you bought a book, you've done something like that. So that number up there is if you guys want to be the only Chem 1 class to have a panel up there in the front of the school. Okay, so what I did is I took the number of you, which is 15, multiplied it by 2, I got 300. Okay, so for those of you that have bought solar merch or bought books, I've subtracted out where you're already at. Okay, so what you have left is the balance, if you want to, and collectively as a class, you need to do this. Say, hey, do we want to be the only Chem 1 class that's going to have a panel in the front of the school? Okay, that's all up to you. That shows you where you're at. So if you bought merch, so if you walked in this morning and you have merch, you get to use these, you've already contributed. The other criteria is that you have to prove to me that you've done something to make the world a better place. So if you want to throw a couple bucks to the solar project, that's fine. If you can say, hey, Mr. Burkamp, I've volunteered, I've done this. Hey, Mr. Burkamp, I've done this. So if you can prove to me in some simple way that you have made the world a better place through volunteering, doing something like that, you can use these. If you gave food at Thanksgiving to the food drive, that counts, okay? So hopefully you all at some point can say, hey, Mr. Burkamp, this is what I've done to make the world a better place. And if you haven't, that's a sad, sad statement. That you've been on this earth 15, 16 years, and it's like, no, I really haven't done anything to make the world a better place. That's then as a society, we have failed you. If you've gone this long on this earth and you have done nothing to make the world a better place, that's worse than what I can teach you as chemistry. So if you want to use this on the test, and if you can honestly say, I've not done anything to make the world a better place, fine. Then you don't get to use these. So whatever you write on these is strictly up to you. So what I would recommend is that on your, if you're not sure, like if we go over some stuff, you all have, through Google Classroom, access to all of the packets, okay? Go back through there. Go back through all of the packets. So if you come across something, you go, oh, sketchy on that one. You have access to all those electronic things. You have access to all of those guided practice. You have access to all the homework, everything that you've ever handed in, I've given back to you. Okay? You have access to all of that. So that's what I would recommend. Now, you don't have to fill these out completely. Okay? So if you have like an electron configuration example, this is whatever you want it to be. If you just want to write, hey, 1s2, 2s2, 2p2, hey, that's all I need to know. Okay? So how you fill this out is up to you. And if you don't, and if you choose not to, go, hey, I've got this. I don't have to worry about anything. Hey, good for you. Okay? That's your choice. So I'm going to give all these out. And then if you want to use this on the test, here's what I want you to do. Now, if you all have the solar merch, you're good. You don't have to put anything. But if you haven't, and you want to use this on the test, so up here on problem solving guide number 1, tomorrow, and you want to use this on the test, this is up to you, You're gonna say, hey, this is what I've done to make the world a better place, okay? And if you wanna throw a couple bucks to the solar panel to get that, that's cool, okay? But if you wanna use this on the test, this is gonna be your criteria. Up here in the top right-hand corner, I'm gonna go around, and if you have this out, I'm gonna look and say, this is where you justify that you have made the world a better place. And it doesn't have to be, hey, I found the cure for cancer. Just be cool, don't get me wrong, okay? It doesn't have to be anything that monumental. Hey, I raked leaves for my neighbor, okay? I gave money to the homeless, whatever it is, okay? So it doesn't have to be anything earth-shattering. So I'm done. So you have the rest of the time, you can finish up that lab, and then start to go through this. The better, and this is personally how I always learned best, was that if I wrote it down, I was more likely to remember it. Okay, that's just the reality of it. The more often I wrote it, the more likely I remember it. That's just me. So, all right, Miles, stop you on the camera.